ISO, the International Organization for Standardization, has a hydraulic system or hydraulic fluid classification system known as the 6743. In this, the ISO attempts to classify in an H category, hydraulic fluids, all the various types of hydraulic fluids, from automatic transmission fluids to fire-resistant fluids to anti-wear and R&O type of fluid. And by that classification, they can clearly identify every single type of hydraulic fluid. Part of the 6743 are 4 classifications of environmentally safe hydraulic fluids. HE, hydraulic environmental. The first one they talk about is the HETG, hydraulic environmental triglyceride, which are your vegetable-based oils. They have the HEPG, which are hydraulic environmental polyglycols, the HEES, which are the esters, and the second S is saturated. At one time they used partially not fully saturated esters, but they found to be much more like the triglycerides in terms of their performance characteristics. And really the ISO is not involved with those anymore. And finally the HEPR, which is hydraulic environmental PAO and related products, which is a fairly new classification. The HEPR, the PAOs, are a top-tier synthetic fluid which are commonly used in today's synthetic engine oils and hydraulic fluids. You can see in this chart the various performance and types of classes of fluids from the HETG all the way through the HEPR. I wanted to throw in one other classification that people talk about, which are the inherently biodegradable products, which are not classified as environmentally safe by the ISO. And what I'll do is I'll go into some of the details, but again, in this chart you can see that the performance in terms of oxidative stability, in terms of elastomer, hose, and seal compatibility vary by the type of classes, as well as water tolerance and various other characteristics. You can see from this slide also the difference in cost of the various type of fluids. All the way on your far left are conventional petroleum oils. Now before we go into costs, I'm sorry, there's been tremendous fluctuation in the cost of hydraulic fluids and petroleum oils. My numbers may be a little bit out of date, but you can see the same relative costing, where a conventional petroleum oil runs between $5 and $6 per gallon. A white oil, which is the inherently biodegradable type of oils, cleaner, more refined, run in the $10, $11 per gallon range. The vegetables are probably in the low teens per gallon range. The HEPR, the biopolyolefins, are in the $20 to $25 per range, and the esters run as much as $35 to $50 per gallon range, depending on the type. So first, talking about the inherently biodegradable fluids. These are not the readily biodegradable. They're not environmental oils as classified by the ISO standard. Typically a white oil, more commonly used with non-metal containing additives, which makes them far less toxic than conventional fluids, but still not as environmentally safe as can be. These offer typically excellent performance, good oxidative stability. The oxidative stability is the ability to withstand heat. They have very low toxicities. They give good anti-wear protection for the most part and are compatible with most conventional sealing materials and elastomers. They're typically lower cost from all the environmental type fluids, but are very expensive as compared to conventional petroleum products. Their main liability, their main weakness is that they are not readily biodegradable. If they spill into the environment, they stay, they're persistent, they do not break down in a timely fashion. The next classification is the conventional vegetable oils, the HETG. As I had mentioned, the vegetable oils have excellent lubricity. They protect against wear very easily. They also are great, highly detergent type fluids, cleaning systems, keeping systems very clean. They are environmental. They're renewable, so every year you get a new batch of them. They're highly readily biodegradable, and they're probably the lowest costing of the readily biodegradable hydraulic fluids. Their weaknesses, you have to be very careful with their operation. All hydraulic fluids, all lubricants in general, last longer and perform better if you keep them clean and dry. More so with the vegetable oils that break down at higher temperature. If you get to 180 to 200 degrees Fahrenheit, the life expectancy of these fluids shortens dramatically. Also, a little bit of water in the system will cause them to hydrolyze and break down and form acids and create wear. So if you're going to be using a conventional vegetable oil HETG type of product, you have to expect relatively short change-out intervals. You must take care that the system operates at a relatively cool operating temperature and that you keep that clean and dry. Not that hard to do in many applications, but in some applications it's virtually impossible. Now, some innovations in terms of additive performance, in terms of base fluids for vegetable oils, have created a category that I call the HETG Plus. That has slightly better performance than the conventional vegetable oils. This can be done by utilizing specific types of vegetable base oils like a high oleic canola oil or a high oleic soy oil that will perform better than a conventional food grade vegetable oil. Also, enhanced additive performance can do that. They offer the same benefits of the conventional fluids, but give much better performance in terms of oxidative and hydrolytic stability, but still have a finite life expectancy. And the temperatures and moisture applications, while a little bit more flexible, are something that must be taken into consideration. These are also significantly more expensive than the conventional vegetable oils. The HEPGs, the polyglycols, are typically synthetic. These type of fluids were designed originally because they are fire resistant and can handle great quantities of water. In fact, most of them are water soluble. These were developed for areas where fire was an issue, such as forging plants, such as metalworking plants, such as foundries, so that if the oil leaked, it didn't create a fire. These products are very, very nice because they operate under a broad temperature range as well, from very cold temperatures to very hot temperatures. One of the problems with these is that they're very, very high in cost. As a synthetic, they become very expensive. Also, they're not compatible with conventional sealing materials and conventional filters. Now, the people who were working by fire and needed the fire resistance understood this and were willing to make the sacrifices and the changes necessary to use a glycol type fluid. But in many applications where you don't want to change out your system, these are not really a suitable alternative. Also, they're not compatible with conventional vegetable oils or even conventional petroleum oils, so a major changeover must be done to flush out every single drop of the old fluid before something can be utilized anew. In addition, these oils absorb water. So you start off with a relatively pure polyglycol fluid, but as the system breathes, it absorbs water and then holds water into the system, causing rust and oxidation and all kinds of bad things associated with water. The next classification are the synthetic esters. As I mentioned, these are the HEES. The saturated esters are much more stable than the unsaturated esters. These are very nice because they give good oxidative stability. They have high degrees of biodegradability. Most of these are readily biodegradable. The limitation to them is they are hydrolytically unstable. they unzip when they touch when water comes in contact with them, and I will explain a little bit more about that in a few minutes. As a result of this hydrolytic instability, there is significant acid formation when it becomes hydrolyzed and seal degradation. The synthetic esters also have a fairly significant temperature limitation, and from what we've seen in the marketplace, they are very, very expensive. As you can see from the slide, the way an ester is made is it starts with a vegetable oil. Actually, it's any triglyceride. And it's combined with an acid and an alcohol. And that forms a synthetic ester, water, and heat. And when you dry the water and you take away the heat, you have a synthetic ester, which is an extremely durable base fluid for a hydraulic fluid. The problem is, in the real world, water and heat get added back into the system, and the reaction is 100% reversible, which means that the synthetic ester will go back to form a vegetable type oil, alcohol, and acid. And then you're stuck with acid and vegetable oil in your system. The vegetable oil is oxidatively unstable, as we've already said, and the acids will create rust and corrosion. So if you're able to keep your system very dry, then a synthetic ester will be a good alternative. But in many of the applications where marine environments or outside environments exist, it's very hard to keep the fluid dry. The final classification is the PAO and related products, the HEPRs. Some PAOs are biodegradable, many are not. The ones that are in this application we refer to as the biopolyolefins, meaning these are olefin-based and they're biodegradable. These products offer excellent durability in terms of an extended life. They has a low cost of usage. They're relatively expensive when you purchase them, but they last a long, long time. Some types of HEPR products claim fill for life. I think that's a little bit over the top, but you can fill for a long, long time. They have very low low toxicity. They're also very compatible with conventional sealing materials. So they seem to be a good choice. They are also hydrolytically stable, which means they can handle a fair amount of water before they start to break down. So they seem to be very suitable for severe environments, high temperature, moist environments.